because the great problem with antimatter is we don't know how to successfully contain it. Because if it touches normal matter, it goes boom. So a lot of work is being developed in like electromagnetic containments.
Okay. So one of the question is, I asked like the same question, what is dark matter? And the guy wrote like, as we know, every form of the energy travels in loop, whether it's small or big. Does light energy travels in, like, he means light, does light travels in loop too?
Does light travel in loops?
Yep, I think he is asking this. Does the light energy travels in loop too?
Well, if you're talking about dark matter and stuff traveling in loops, that makes me think of like you've got this big gravitational entity here, like maybe a star, and light will actually like bend around the star. So it won't like loop all the way around the star, but the path of light is actually affected by gravity. Which is amazing. And that's a confirmation of general relativity. Like that was confirmed during an eclipse of Mercury, like about 100 years ago. The light bent around the very massive Mercury. And, that's proof that general relativity is a thing and light cannot escape the forces of gravity.
So when we talk about gravity, so do we consider them as like particles? Do we say like as like gravitons?
Yeah, that's a good question. I'm not sure if gravitons have actually been proven to exist or if that's just the particle interpretation of gravity. It's certainly nicer for the standard model and expanding it if we have some sort of force carriers, and the graviton carries the force of gravity.
Okay. Oh, someone asked like, what can be the uses of dark matter if we are able to extract somehow? Like, what are the applications? Like, how can we use them in our benefit? I guess they're asking.
That's a fantastic question. I am not actually sure about that, but I have a bunch of friends who are dark matter theorists who might have better answers on that. At this point, it's more, we know something's out there and we're trying to figure out what it is. As far as actually containing it, I feel like there's probably not going to be many terrestrial applications, but I can imagine astrophysical applications for, when we all have spaceships and we're rocketing through the stars. You could maybe do a dark matter concentration to like help you get into orbit around something, because you will naturally, like the spaceship would naturally like go towards the gravity. But that's very like science fiction-y.
Yeah.
It's so far beyond where we are right now. It's like we've known that dark matter exists for like Zwicky postulated it about 80 years ago, and then Vera Rubin actually confirmed it like 50 or 60 years ago. So it's, even though decades are a long time, it's still very much in its infancy, and we have to figure out what it is first before we can figure out how to use it.
Because the thing is, like, you're talking to engineers, so they're more interested in the application, like how we can use them.
Yeah.
That's how I think the question came out.
Yeah, no. So if you can build a detector and actually find it, then we can figure out how to use it.
Oh yeah, for sure. So another question we came in, like, why there is no spin-dependent analysis of dark matter, indirect search, dark matter annihilate to SM particles. Did you get it?
So I'm guessing SM particles would be standard model particles.
I guess so, yeah.
And Yeah, that one's a little beyond my knowledge with the current dark matter searches.
Okay, okay,
And
okay.
I feel like that one just goes back to we still don't know what it is enough that we're
Mhm.
having trouble designing experiments to try to actually detect it. Um, but if any of you all have ideas on how to design better experiments, try to get an internship with with the university or a company actually doing it, because uh,
Mhm.
dark matter theorists are kind of at their wits' end and would love some fresh input.
I guess so, yeah. So okay, moving on. How did the dark matter and the dark energy like originate? Did they get along like the starting with the Big Bang, or like how did they like? What's the basic origin? I think they mean to ask.
Yeah, so that's a great question, and we're not entirely sure. The current assumption with the cosmological model that we have, the lambda CDM model for
Hmm.
cold dark matter, is that yes, everything did originate with the Big Bang, and there were like little clumps of dark matter that were just slight inhomogeneities in
Hmm.
space,
Hmm.
and the regular particles just kind of were gravitationally attracted to that, and then inflation happened and spread everything out around across the whole universe, and these little overdense regions became, quite stretched out overdense regions, and that formed the cosmic web along which we see all the galaxies today. Dark energy was probably around since the Big Bang. However, its influence has been increasing ever since. So that's one of the theories of how the universe could end each other. It's like an anti-gravity. It's a repulsive force. And everything just gets like spread out until it's all cold and distant and there are no more stars in the sky, which is kind of a depressing thought. But also bear in mind that I've said we know very little about dark matter. We know orders of magnitude less about dark energy. I've asked my theorist friends if they want to speculate on dark energy, and they just kind of laugh and say there's not even a basis there to start speculating on. So there are more dark energy searches coming online this decade. Like DESI is really cool. It's a dark energy search. I forgot what the I stands for. So hopefully we'll get some more insight onto that. But it's an even more nascent field than dark matter.
So this study is still like very early stage, so people are still working on the depth.
Very early stage, yeah. Which is great for engineers. You can really get in on the ground floor of trying to build detectors and
That's
just
great.
kind of narrow down that parameter space for how to find this.
Yep, yeah. Let's see who does that. Maybe someone
Exactly.
among us is
That
there.
would be amazing.
That would be yeah, that would be truly amazing. It's
Yeah,
like more exciting work.
I wanted to do dark energy work. Um,
Hmm.
but I was basically told, yeah, there's not really enough there theoretically to do. So I started doing dark matter.
Okay, okay, okay. So we have a question like, is there any effect of dark matter on the orbital speed of the sun around the center of the Milky Way? So I think like the motion of the sun, like it's revolving around the galaxy. So is the
Yeah,
dark matter having any effects on that?
that's a great question. We usually don't think of dark matter as having effect on single stars. It's more like the rotation curve of the entire galaxy, which is stars closer to the center of the galaxy are moving just as fast around the galaxy as stars further out from the center, like much further out from the center. And the fact that the stars very far out are moving as fast as the ones closer in means that there's more matter out there than we can see, which is the standard rotation curve argument for dark matter. The sun is about like a third of the way out from the center of the Milky Way,
Mhm.
so dark matter has some impact on its speed, but I think it's probably only moving like slightly faster than we would expect, rather than much faster than we would expect.
So it's just a like a normal calculation we did, or we have a verification for that, or we just.
Yeah, it's a normal calculation, and that was very similar to what I was doing in my first research project. And then I got to University of Maryland, and
Mhm.
we did an astronomy lab, like a whole week lab on calculating the rotation speeds of various stars due to dark matter interference.
Okay,
So
okay. So
if you want to transfer to University of Maryland, you can do that lab.
okay, let's see. Like I'm in my like final year, so I'm just mechanical senior.
Hey,
So
if you want to go to grad school at UMD, you could teach that lab.
oh, okay. Maybe let's see. Like if I got an opportunity, and because there's a lot of work when we are applying to the grad schools in like foreign anywhere like USA, Canada. So
Absolutely.
yeah,
Yeah.
there's a lot of work to be done. Like a lot. So we have to make applications and SOPs and English tests and all of that. So we have to plan a
Yeah.
lot for that.
Yeah,
And
I one of my good friends in the astro program at Hopkins is from India, and like the
that's
amount of work he had to do just to get here is insane.
yeah. Also, like a lot of people are already applying from India, so there's a big competition. Like even in the field of
Yeah.
astronomy, there are like a lot of people interested and they are applying. So okay, moving on. Like okay, we will take some dark matter questions after, but I just want to move on to your research work which you did. I think back in 2019 you were in like the Harvard Community College. Were you there? Like oh no, sorry, maybe in University of Maryland. Uh,
Yeah, in 2019 I was at the University of Maryland and Space Telescope in the summer.
yeah. So what the work I found is like the redistribution of metals in the simulated Milky Way.
Yeah,
So
that was at Space Telescope.
okay. So this was your the second research work after the Howard Community College, right?
So I did like 5 research projects at Howard Community, and that the tracing metals was my second research project at
Uh-huh.
Maryland. I have
Okay.
been very busy.
You've been very busy. Yep. Yeah. So, if I ask you, like, what was your basic part? Were you drawing, like, making simulations for the galaxy, or?
Yeah, so I joined the Foggy group for my summer internship, and that
Uh-huh.
stands for Figuring Out Gas and Galaxies in ENSO. And
Okay.
ENSO is a hydrodynamics code. So you take all of your hydrodynamics equations and you
Mm-hmm.
program them,
Mm-hmm.
and then you basically use that to grow galaxies and figure out how
Oh,
they evolve with time.
so it's all the computer algorithm you're talking about, right?
Yeah, yeah.
So, what software, like, what's the interface you're using, like, for making that Enzo code work?
I just so the ENSO code runs on Pleiades, which is NASA's supercomputer. And
Okay.
then we take the outputs of that and we just analyze them with Python. So if you have
Oh.
a decent understanding of programming with Python, it's actually very
Mhm.
easy to work with.
Yeah,
You
most of the
just
students over here know Python, I guess. Yep.
yeah. So that would actually be my biggest piece of advice: is no matter what you want to do with your interest in engineering, comp
Mhm.
sci, astronomy, learn Python.
And
Just
that
become familiar with it.
it's used everywhere because it's the basic, very easiest one, and I think very useful. So, okay, so when we talk about the metallicity, I guess I'm saying the word right, metallicity, right?
Metallicity. Yeah.
Metallicity. So metallicity. So when we say about the metals, so what kind of like state of metals we are talking about in the
Yeah.
galaxy?
All right. So here's a hot tip. Astronomers are weird. We call everything that wasn't formed at the Big Bang a metal. So the periodic table of elements for an astronomer is you have hydrogen, you have helium, and
Yeah.
then literally everything else is a metal,
Okay.
which is that's what we do. So by metals, we literally mean everything that's not hydrogen and helium. And
Uh,
why are these important? Because those elements weren't formed in the Big Bang, they must have been formed in the stellar cores ever since. So metals are formed by stars.
so they are just formed like through the stars after the fusion and all the reaction
Yep,
activities, but not from the Big Bang, right?
correct. Yeah, they're formed in the late stages of stars. So, like the sun, it shines by converting hydrogen into helium. At some
Uh-huh.
point in the very distant future, we're talking like 5 billion years from now, the hydrogen will run out and the sun will start fusing helium into carbon. And as the fuel source continues to deplete, you start fusing heavier and heavier elements until, if you have a really massive star, it goes supernova and just explodes those elements through the universe.
Okay, okay. So
And that's how
basically,
we get elements everywhere.
so all the metals you're talking about, like distributed in the galaxy, are coming from the death of a star, basically, right?
Yes, yeah. So, as
Okay.
Carl Sagan liked to say, we are all made of star stuff,
Yep. Yeah, yeah, yeah. Each and everything is made of stars. Yeah.
which is
So,
just fascinating.
yeah, that's very much. So, what you find out, like, what was your work? Like, what you found the distribution, like, how's the pattern forming, or like what? Do you find a pattern or
Yeah,
something?
so this was based on observations where we're tracking various isotopes of elements,
Mm-hmm.
and that tells us like if you track oxygen 6, that can trace like where all the oxygen ions are. And what was found was that there are way less metals in the galaxy than there are supposed to be, given the star formation history and the supernova rate. So
Okay.
what I did was, so Foggy is really good at looking at the circumgalactic medium. So you have your stars that form
Mm-hmm.
the main galaxy, and you have your interstellar medium, which is the stuff like directly in and around the stars. And then you have the circumgalactic medium, which basically goes out to encompass the entire dark matter shell that surrounds galaxies. So what I did was I looked like at the very outskirts of these galaxies and found that the metals were escaping the galaxies. It's like they're just hanging out there on the very outskirts of the galaxies. And this is evidence of galactic recycling, where you have a supernova that blows out these elements and they're at the very fringes of the galaxy. And then as things settle in the region, those elements drift back into the galaxy and form new stars.
Okay. So when you said the interstellar medium and the circumgalactic medium, like, I didn't get it. What's the difference between those two?
Yeah, it's not something that has a clearly defined boundary. Usually it's defined by temperature and density.
Uh-huh.
So the interstellar medium is more towards the center of the galaxy, and that's very cool and dense. So it's
Okay.
the stuff just between stars that you usually think of when you see a pretty galaxy image. You see all the light in the center. That's the interstellar medium. If you move to the outskirts of the galaxy, where the stars appear dimmer and just kind of fade off into black, out there is the circumgalactic medium, and the temperatures are very hot, like 10,000 Kelvin and above. And the density is very low. You would have like maybe one hydrogen atom per uh, cubic meter. So it's like
Oh.
better than the best vacuum we can create on Earth. So it's very difficult to see that because it's very hot and very tenuous and there's not much there. But you can take observations and make
Mhm.
simulations based on those, and then you can explore the simulations, which is what I did.
Oh, it's a lot of work, like a lot of terms, and okay, we need to understand everything, and then
Oh
okay,
yeah,
okay. But I got a pretty much of idea. I think everyone got it. Okay,
it's a
so
complicated idea.
yeah, it's a complicated work. So, like the all the future work you did, like after this work in 2019, is it related to this the same work with the galaxies and all, or like
It's similar. I'm still using simulations, but
okay,
instead of tracing the metals, I am now looking at like so I colloquially call it I'm tracing when galaxies get fat because I'm looking at their physical thickness through time. So if you picture like a
oh,
nice edge-on galaxy, you have like the bulge in the center and then a thinner disk that goes out,
mhm,
and you've got older stars forming the bulge and younger stars in the disk. And I'm tracking like when the stars actually formed that bulge and how thick galaxies were about half the universe's age ago. So I'm using data from the Hubble. I'm
okay.
applying for time on Webb and
Mm-hmm.
um, backing all of that up with simulations. Like, hey, here's what the simulations say. Now we
Mm-hmm.
need observations because this is our prediction and now we need to test it.
Okay. So when you get the data set, as you said, you get the data set from the Hubble, right?
Hmm.
So I think many other students in the same university or maybe from other universities, they also get the same data set from the Hubble.
Yeah,
But I think they put on some different parameters to test that. Is it like that?
yeah,
Or you
yeah.
do the,
The
or you do like the you put all the parameters, or is like many more students are also working on the same data set but with different parameters and it's like that.
So the data is all public. Like anybody can access
Oh,
it
okay.
as long as you have a computer.
Mm-hmm.
The nice thing is that several teams already like reduced and cleaned the data and just said, here's all the data, here's all the parameters, have
Mm-hmm.
fun. So I'm
Okay.
looking at parts of the data with some parameters. Um, I don't know of any other students who are working on this same data set at my university, but
Mm-hmm.
certainly other people are looking at it's the candles data set. Um, Not sure if that means anything. It was taken like 15-ish years ago, but certainly it's a very well studied data set. I'm just analyzing it in a slightly new way. So that's a fun thing is that once you have a really good data set, you can analyze it in lots of different ways to learn different things.
Okay, that's great.
It's a lot.
Yeah, it's a lot of things. It's a lot of work to do. Okay, so moving on, we have some questions from gravitational waves. So if we really identify the gravitational waves, so what more scope of like applications or maybe how the gravitational waves would be useful for more astronomy research, like how we can use it further.
Yeah, so gravitational waves are just another way of looking at the universe because everything that we know about the universe right now comes from studying the electromagnetic spectrum.
Hmm.
We go from like microwaves and radio waves all the way up to X-rays and gamma rays, but that's just one set of information. Now, with gravitational waves, we can see the universe in a whole new way. It's kind of like we were seeing everything in black and white, And then all of a sudden we got the ability to see color. So there's so much more information there, that really we're just scratching the surface because we've only had about a decade of gravitational wave astronomy, but it's already opened up a lot of doors about understanding like the final stages of stars. And once we get like LISA, as I mentioned, the huge gravitational wave detector in space, we're just going to, it's going to kind of be like Webb, where there's a new groundbreaking discovery every week, because this is at the very ground level, and there's a lot of low hanging fruit that all we need to do is just be able to see in gravitational waves, and we'll be able to find really cool things.
Hmm. Okay. So more questions are coming like does the dark matter and like the gravitational waves, do they have any uh, mere physical property other than like interacting with light? Any other property do they have?
That's a good question. Not that, so gravitational waves, um, they do interact with light, but like very weakly.
Mm-hmm.
So you need basically something outside of the electromagnetic spectrum to be able to actually see them. Like light can tell you that they're there because of the stretching and the contraction,
Mm-hmm.
but to create a like an actual gravitational wave map of the universe is going to require just like a whole new understanding. Dark matter doesn't interact with light at all, so we need something like beyond the electromagnetic spectrum to be able to see it, because it only interacts gravitationally.
Hmm. Okay. Okay. Uh, Few more questions we have in the live chat. Like, is the dark matter and the antimatter the same? Like, do they have any similarities between them?
That's a um, a question that's being worked on in theory right now. They're not the same, but they might have similarities where dark matter could have like um, some characteristics of
Mm-hmm.
current particles, much like you have an electron and a positron. There's also supersymmetry, where you have
Mm-hmm.
a supersymmetric version of a particle, and that is one of the theories for dark matter. It's unfortunately kind of fallen out of favor because the parameter space for where that dark matter particle would be is so constrained now that it's not very likely it'll be there. Uh, but it's a cool idea, and I personally would have liked it if it worked.
Okay. So this one, scary question. So the question says like, is there any chance by which like our Milky Way galaxy can collide with another galaxy in future time? And if it
Yes.
happens, then what's the consequences we can get?
Oh, this is such a fun question. Thank you for asking. Yes. In the distant future, the Milky Way and our nearest huge galaxy neighbor, Andromeda, or
Mhm.
M31, will collide. However, because space is mostly empty, it's not gonna do anything, except maybe give us a nice show in the night sky, because there will be more stars visible, because the Andromeda stars will now come and mix with the Milky Way stars. But you think of galaxies as these super dense things, and they're going to collide, and stars are going to be exploding everywhere. And that's not actually the case. Various simulations have shown that you have a better chance of getting struck by lightning than something colliding with the sun. Um,
Okay.
so the stars will just like it'll get a little more crowded in the solar neighborhood, but it won't really impact us. There will just be more stars in the sky. There will be more supernovae going off, but not near us. We just might see, oh, look, pretty bright supernova in the sky. Cool. But
Uh,
we'll be completely safe.
so okay. So what? people imagine basically like the normal people imagine. I also imagine like if the galaxy is gonna collide, is there a possibility like the main interstellar mass in the center of the Milky Way and the Andromeda both are they gonna form like a binary galactic system or something like that? Is that gonna happen?
Yes, that is what the simulations show. So you've got all galaxies, at least that we know of, have a supermassive black hole in the center.
Mm-hmm. Mm-hmm.
So what projections show is that Andromeda's black hole and the Milky Way's black hole will probably form a binary black hole system.
Okay.
And at that point, they are likely to merge at some point because they'll just keep circling and circling until they get so close that they can't
Uh-huh.
escape each other's gravity, and then they just become an even bigger black hole. And when that happens, there will be a huge release of gravitational waves from the black hole merger.
Uh-huh.
But other than that, not really going to affect us. Lots of cool science, but no impact on our day to day lives.
Okay. It can become, although it can become like a fantastic science fiction movie if that happens in a.
Oh yeah, if you get a rocket ship and you just like park right outside the center of the galaxy, right outside
Mhm.
the gravitational the Schwarzschild radius,
Mhm.
then you'll get a fantastic sight of all these stars falling in, and then
Ah,
this huge burst from them merging. Uh, that would be amazing. I would love front row tickets for that, as long as there was a guarantee that I would not also get sucked in.
yeah. I hope someone makes a movie about this dystopian future where we can get,
That
right?
would be fun.
Yeah, that
There's
would
so
be
much
really fun.
untapped potential for science fact-based science fiction movies.
Yeah, like, because most of the movies we also know are like The Martian, The Interstellar, and like
Mhm.
we have like a lot of more concepts on which movies can be made. Like there are a lot of ideas. I don't know. We need more work on that.
Exactly. Yeah, no, The Martian and Interstellar are the two movies that I recommend to people who want to watch a movie that's actually scientifically accurate.
Hmm. Okay. Oh, okay. So one more crazy question is like, is there any particular work going on in um, time travel, like, or like, are the astronomers working on that? Although it's like a very paradoxical concept. Everyone knows that.
It's incredibly paradoxical. There are some theorists working on that. You have the problem of needing to reverse entropy. So instead
Mhm.
of time's arrow just pointing in one way, you need some way to violate the second law of thermodynamics and make entropy go down to be able to travel back in time. That's more of an engineering theory thing, though.
Mhm.
That's not something that astronomers are really working on, because astronomers have their own version of time travel, which is the fact that light takes time to travel.
Mhm.
So if you're looking at a star that's 65 million light years away, you're seeing that star as it was in the distant past. Someone on a planet around that star looking at Earth
Mhm.
wouldn't see us.
Yeah.
They would see the dinosaurs.
Yeah. It was the distant past. Yep. Yeah.
Yeah. So there is a version of time travel with time dilation, where if
Mhm.
you're like very close to the speed of light, time slows down around you. But like going back in time and riding a dinosaur is not something we're actively working on right now. But that does mean it's an open area of research if anyone has any thoughts on that.
There's also like a hypothetical experiment where I think the Stephen Hawking told, which like if we build a track around the Earth and a train is traveling around the like it's taking a
Yeah.
full revolution of Earth, like in I think seven revolutions in 1 second, I guess.
Mhm.
So that's so fast that the time will be slowed down on the people traveling
Yeah.
in the train. So when
Yeah.
they get out from the train, they will be in the future.
Yeah.
Yeah, that's
So that is a time machine for going forward. We just
Uh-huh.
would have to have the infrastructure to support, a hugely fast train track around the Earth, which is a thing for future engineers to design.
Mm, okay. Oh, so another question would be, okay, so one more question in the live chat is like the dark matter and the dark energy, are they different or it's like the same thing?
Yeah, so we believe that they're different. We don't know enough about either to quantify those differences.
Mm-hmm.
Dark matter seems to be a particle, something that has mass and takes up space
Mm-hmm.
and attracts things gravitationally to it, whereas dark energy seems to be a force, kind of like the polar opposite of gravity and the opposite of dark matter, where it seeks to repel things. But we don't think that, um, much like a graviton, the force carrier wouldn't have mass, it just transports energy.
So when we say dark energy, we actually don't mean energy in the terms like when we say energy in the physical terms, we actually mean like E equals to mc square. So energy is matter. So it doesn't relate on the same relation we say. It doesn't.
We so that's something that we are trying to figure out.
Mm-hmm.
We feel like it should because E equals mc squared defines all of standard matter and energy,
Yep.
but we
Yep.
call dark matter and dark energy dark because, for one, we can't see them. They don't interact with the EM spectrum at all. But another, they're dark because we haven't uncovered their mysteries yet. So they may actually have their own different, like, matter energy relations that we need a future Einstein to come up with.
Okay. Okay. So one more question: is the universe actually expanding? And if it is, then where is the extra space coming from? Like, if the all the universe is expanding, then how are you getting more space, like for the expansion?
All right, so for the universe expanding, I have to rep my university here, because Adam Rice and his team at Johns Hopkins did the experiment that won the Nobel Prize for determining that the universe is expanding. So yes, the universe is
Okay.
expanding, but
Mm-hmm.
um, it's kind of complicated to think about, like, what is it expanding to.
Mm-hmm.
So there's kind of an analogy where you can imagine a hotel, and this hotel has an infinite number of rooms,
Okay.
and then they decide to add two more.
Okay.
So they still have an infinite number of rooms. It's
Yeah,
just bigger than it was before.
but it
It's
doesn't
it
make a
like it blows
difference.
your mind. Yeah,
Oh, okay. 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 So everything we consider is infinite. So, but
yeah. We have an observable horizon where light has only been traveling to us for so long that that's as far as we can see.
mhm.
But the universe is expanding beyond that. We just don't have the capacity to see it yet, which is something that maybe with gravitational waves and studying neutrinos, those are different ways of looking at the universe, and maybe we
Mhm.
can expand our horizons.
But the universe can't be really said infinite, right? Uh,
Um, it's that you get into like different types of infinities there.
mhm.
Like the universe that we can observe is finite,
Yeah.
but we think that the universe itself is infinite.
Mhm.
Okay,
Okay.
did I blow everybody's brains? Like this is
Yeah,
this
I
is
think so.
insane stuff.
So is there any theory like when we consider like this universe expanding and where does all space come from? So do we also get this multiverse theory? Is it true? Like people are researching on that, or
Yes.
is just a
People
term?
are actively researching a multiverse.
Oh,
Maybe not like in the way that Marvel is showing the multiverse,
yep, yeah.
but I have a friend who's working on string theory, which
Uh-huh.
is, like little pocket dimensions of time. Like when you get into multiverse and string theory and other dimensions, you're straying into science fiction. But as Arthur C. Clarke said, any sufficiently advanced technology looks like magic to someone who hasn't seen the progression of it. So you've got these science fiction ideas that sound just absolutely fantastical, like the multiverse, pocket dimensions,
Hmm.
and then, maybe in another couple hundred years, we're just commuting to the multiverse every day. Like, oh, I don't want to work in this universe. I'm going to go work in that universe instead.
Ah. So it's again a lot of like it's a lot dependent on the dimensions. So are we working on the because the basic explanation, if I would say, like because we believe that we have more than four dimensions. I guess like, I'm considering fourth one as
Yeah.
the time. So
Yep.
the basic example I would like to tell all the audience is like I read a one book. I think it's book or it's a movie. I don't know. It's a book. I think called as Flatland. So the Flatland explains. Ah, okay, you know that.
No, I
So
read it when I was in fifth grade. Yeah, that's
oh,
great.
you already read that. Okay, okay. So those creatures see everything in the two dimension, but when they see it, they see it's like a. If I see a triangle from the top side, it is like kind of a two dimension. But when the creatures see themselves, they see themselves as single line because it's like the projection is as a single line. So on the basis of that, can we say like we have more dimensions, but we just can't see them? Like the creatures from that dimensions are seeing us, but we can't see them.
Absolutely. So that is another kind of creepy and potentially scary thing. But also very cool to think about is that there could be other dimensions that we just can't see at this point.
Okay.
And
So
maybe
is there any work
someday,
going on that?
I I'm not sure how active the work is. I think it might be more mathematical theory, and
Hmm.
my friends
Yeah,
in math
true.
theory constantly remind me we're about 500 years ahead of reality. So
Hmm.
maybe in 500 years we'll be able to see the other dimensions. They're
Yeah.
the ones working on the different types of infinities too. It's insane.
Ah, your friends are more into theoretical physics, I believe.
I
Cause
have uh, I have friends building rockets. I have friends who think about what a dark matter star would look like. I
hmm.
have friends who investigate what would happen if you fall into a black hole. I have friends who are building dark matter detectors. I have friends who write papers about different types of infinities. It's once you get into the academic world and you get to know everybody, you go, wow,
Wow.
there's really
Yeah.
weird stuff going on.
Oh, if your friends like get together in one room, there's a lot of IQ, right? In the whole room.
Oh yeah.
And
Oh yeah.
I can just imagine like all of them discussing with their domains and coming up with some crazy conclusions.
Oh yeah, no, it's really fun to get all together. And then you have like I've got another friend who's working on the asteroid prevention system, a way to
Sorry,
keep
what?
Earth safe. I've got a friend working on an asteroid prevention system. So if an
Oh,
asteroid
okay.
looks like it's on a collision course with Earth,
Mm-hmm.
he's working on a program that would safely deflect the asteroid so we don't get hit. So that's a very practical thing. And I just would love to get him in a room with my friend who's working on what if there were primordial black holes everywhere? And just not applicable at all, very
Uh-huh.
applicable. Let's put those together and see what happens.
Mm, the guy you told about like he's trying to deflect the asteroids. Is he making some kind of death ray or something?
No, it would be more like using gravitational forces to like push and pull it away to just deflect it. There was the DART mission that successfully deflected an asteroid and its little moon
Okay.
a couple of months ago. I think it was like in August, and his group was involved in that.
Oh, okay. It's this. That's a lot of things I didn't know about this. Like the people already have deflected asteroids.
So it's really cool.
Yeah. Okay. Um. So what do we have here? What do you have any? Do you have any say on the Fermi paradox?
No, I don't. That's a lot of fun to think about, but um, I mean, there's the usual flippant answer, which is, yeah, they saw what we were like, and we're like, nope, we're just gonna. Earth is a backwater. They need to get their act together first before we approach there. I don't think there are actual aliens hiding in like the basements of government facilities. I hope at some point we can reach aliens, but the thing about it is that space is so incredibly vast and there are limits to how fast organic life can travel that it's just like, okay, so I'm here on the eastern shore of the United States. If I wanted to
Mhm.
go visit India, I couldn't just jog down the road. I'd have to like book a flight or drive somewhere to get a flight or like
Mhm.
drive and take a ferry, and it
Mhm.
would take me a not insignificant amount of time to actually get there. Now multiply that by the fact that light itself takes 8 minutes to get from the sun to Earth.
Yep.
So the nearest star to our sun is 4 light years away.
Mhm.
So if there was a civilization around that star, well, they could get here in 4 light years, but they can't travel that fast. And
Mhm.
we've only been broadcasting like radio signals into space for about 100 years.
Mhm.
So are the bubble of people who potentially can know about us is continuously expanding, but we
Mhm.
haven't encompassed many star systems yet. So I hold out hope for the future, but I don't I don't think there are any aliens here yet, but I would sure love it if there were.
Mm. Yeah, you're true. Like the nearest star after the sun is like the Proxima Centauri, I guess.
Yes, yeah. That's very good. It's the Alpha Centauri star system, but Proxima is the closest one.
And it's still like 100 light years away. Is like that, right?
It's 4 light years away, but it's like very I think it might be like 100 kiloparsecs. Like it's
Okay,
far. It's
it's far.
We would need a generation ship to get there.
Mm-hmm. Okay. Okay, to just sum up with the one last question we got is, uh, Dark. Do you what's your point on what is this Big Crunch? Are you
Yes,
getting?
the big crunch where the universe is expanding and expanding and then all of a sudden it just starts contracting and because of gravity it gets faster and faster and then everything just collapses
Mhm.
into a singularity. Um, That's very interesting, and I can certainly see the theoretical background for that. Like, oh, there's only so far that the universe can expand to. We are currently not in any danger of that because, as the teams at Hopkins keep showing, the universe is not only expanding, the expansion is accelerating. So
Mhm.
we haven't reached a point where the expansion has slowed down or even
Mhm.
gotten to some sort of equilibrium to like turn around and crunch back again. So yeah, I don't actually spend a lot of time thinking about the end of the universe. I do like the idea that like everything can uh like collapse to a singularity and then reform, and so the universe just like keeps reforming itself like a phoenix.
Mhm.
Because that to me sounds nicer than the big freeze where everything is just so far apart that you can't do anything anymore. That makes me feel sad and lonely. The big crunch, at least, I think, oh, well, cool, my atoms will be
Everyone is
around in
here.
the
Yeah, yeah.
next
We
cycle.
are surrounded with the people. There's a
Yes.
possibility that India, like all the people over here, are coming closer to
Yep.
you if the brick
Yep.
crunch happens. Okay, okay. That's quite a big discussion we had, like from around 1 hour. So I think that's it. Like we had like a lot of discussions. We talked about, I don't know, dark matter and some of your research work and black holes and stuff and all that.
It
So
was a lot of fun. I
yeah, it was
really
it
love
was
talking science.
yeah. That's good. That's good. Like we all needed this kind of discussions to get some of the queries we have, and I think now we can wrap up with this discussion. And Kathleen, thanks a lot for joining in and giving your like a lot of precious time and telling a lot because we got new perspectives now. We think in a new way. Like me, I have a lot of interest in astronomy and I've studied a lot, but I still got to know about like a lot of things. Especially, I didn't know about the fact that astronomers think like not think, but they conceptualize hydrogen and helium the separate and the metals as separate. I
Yeah.
didn't know that. This
Yeah,
was
we're a silly bunch.
yeah, this was like the astronomer stuff. They just talk about this language. So okay, I was thinking metals, so we think metals as the engineering way.
Yeah, no, astronomers define them differently than literally anybody else. But
Yeah,
thank you so much for having me. This was great. You have my LinkedIn contact information. Feel free to spread that. I would love to connect with you all. And if you have questions, just feel free to message me.
yeah. So I guess that's it. And do you have any last piece of advice, like for all the engineering undergrads who can like join astronomy? Like, what do you think? They just need to stay focused on their study work and be interested. Is it like that, or anything you can
Yeah.
say?
Well, I saw a question about book recommendations. So,
Hmm.
absolutely, if you have not read The Martian by Andy Weir, drop whatever you're doing and go get a copy of that. His other two novels, Artemis and Project Hail Mary, are fantastic for realistic science fiction. Project Hail Mary, especially, touches on a lot of things that we were talking about, specifically contact with aliens and general relativity and space travel. So I would highly recommend all three of those. I watch Star Trek all the time, so if you haven't watched Star Trek, that's you should definitely go watch Star Trek. It's fantastic science fiction. Generally, if you're an engineer, a computer scientist, a chemist, there is room for you in astronomy. Astronomy is all fields just projected like off of Earth. So you can be, I have a friend who's an astrochemist. She studies the abundances of chemicals in molecular clouds. I
Hmm.
have a bunch of friends who are building the rockets that will get us the data or take us to the moon. I have a lot of comp sci friends, and like I do this. I spend a lot of the day programming. So whatever you want to do, there is room for you in astronomy, and all you have to do is try to reach out and make some connections. And I just saw a request for me to type books, so I could do that. Let's see. I can do that. Okay, so The Martian, Artemis, and Project Hail Mary. Ooh, I also see a question about uh, wormholes. That's fantastic. That's more science fiction at this point because I actually talked to an actual gravitational wave astronomer about them who was like, "Yeah, we're not there yet." Um,
Hmm.
the conventional thinking for wormholes is that they connect 2 points in our universe. However, there is a potential that you could end up in a parallel universe. So
The term used is like
that
the Einstein-Rosen bridge, I guess. Yeah.
exactly, you would need to better understand the Einstein-Rosen equations,
Mm.
which people are working on, but it's challenging.
Okay. Okay, so you had the books, right? Andy Weir's The Martian, Artemis Project
Yes.
Power Project. Okay. So I think we can wrap up, and if you have any more questions, then if we have more questions from our audience, like related to astronomy, I think we can arrange one more session in future. And
Mhm.
I hope we can get more of it. And yeah, so that's it. I think we all learned a lot, and thanks a lot, Kathleen, and for
Of
joining
course,
in.
here I can also like type my LinkedIn,
Okay, yeah, yeah, for sure, yeah.
yeah, in the ah, it's not working quite well right now, but there we go. Okay. So this is my LinkedIn, and if anyone wants to connect and chat, I am at the beginning of a busy semester, so if I don't reply for a couple of days, just like send me another ping because it probably got buried. But I'm happy to chat about this, about opportunities
Hmm.
for further research, and just thank you all for coming. It was lovely chatting with you and exploring science together.
Yeah, thanks a lot. Thanks a lot, Kathleen, for joining in, and happy Friday, cause you have just began with your day, and
Yes.
we are moving
And
towards the end of the day.
yeah, good night and have a great Saturday, everyone.
Yeah. Okay. Good night.
Thanks.